Hello and a huge welcome to all you students of mathematics in the modern world. Today, we're basically becoming data detectives. We're going to go on a little investigation to uncover the secret stories that are hiding inside our data. Look past just the surface and find out what these numbers are really trying to tell us. So, let's kick things off with a bit of a mystery, shall we? Imagine you've got two different classes, and they both have an average quiz score of 75%. So, does that mean the students in both classes are performing pretty much the same? Well, not necessarily. See, an average, or the mean, as we call it only gives us the center point. It doesn't tell us the whole story. It leaves out a huge piece of the puzzle. Are all the scores bunched up together, or are they all over the map? Right, so if we really want to understand a set of data, like those class scores we were talking about, we've got to look beyond just that one single center point. We need a way to measure its spread or dispersion. Basically, are the scores all huddled together around the average, or are they just all over the place? Answering that question, well, that's where the real understanding begins. And to do that, every good data detective needs a couple of essential tools in their toolkit. And our tools are called variance and standard deviation. Trust me, these are the powerful measures that are going to help us put a number on that spread and crack all of our statistical cases. Now, what's really interesting is how these two tools are connected, but there's one key difference you have to know. Variance, it gives us a number for the spread, but it's in what we call squared units. Think points squared. It's kind of weird and abstract, right? But standard deviation, now that's the hero here. It takes that weird number and translates it back into the same units as our original data, just plain old points. And that makes it so much easier to actually understand and talk about. And the connection between them, it couldn't be simpler. Seriously, you just calculate the variance first, then you take the square root of that number, and boom, you've got the standard deviation. It's really that straightforward. Okay, before we start using these awesome new tools, let's quickly crack the code on the symbols you're gonna see. Think of this as our secret decoder ring. Once you know what each symbol means, like mu for the mean, or that cool sigma for adding things up, the formulas will make total sense. No intimidation here, I promise. All right, team, it's time to open our first case file and actually put these tools to the test. We're starting with what's called ungrouped data. That just means we can see every single individual score. So let's see what we're working with. So here they are, our first set of clues. We've got the scores from 9 different students on a 40-item quiz. And just by glancing at them, you can tell they're pretty spread out, right? We've got a high of 35 all the way down to a 10. Our mission, should we choose to accept it, is to put an exact number on that spread. To crack this case, we're going to follow a simple 5-step process. It's a super logical path that'll take us right from these raw scores to our final answer. Just follow along with these steps and you'll see you can't go wrong. Okay, let's put this plan into action. First up, step 1, we add up all the scores and divide by 9 to get our mean. That comes out to 22.33. Got it? Cool. Now look at the table. We're moving on to steps 2 and 3. For each score, we figure out how far away it is from that mean, and then we square that distance. Now, why do we square it? That's a great question. We do it so that the negative distances, the scores below the average, don't just cancel out the positive ones when we add them all up. This way, every single score's distance, whether it's high or low, counts toward the total spread. And now for step 4, we take all those squared distances, add them up, which gives us 612, and then divide it by our 9 students. And that number we get, that's our variance, 68. It's basically the average of all those squared distances. Okay, and now for the final step, the big reveal. We take the square root of that variance, 68, to kind of undo the squaring we did earlier. And what do we get? Our standard deviation is 8.246. And just like that, case closed. But wait, what does that number, 8.246, actually mean? Well, it tells us that, on average, a typical student's score was about 8.2 points away from the class average of 22.33. See, it gives us a really concrete, standard way to talk about how spread out these scores really are. Excellent work, detective. Seriously, you've totally nailed ungrouped data. So let's level up and take on a different kind of case. This time, we're dealing with grouped data. This is what happens when you don't have every single individual score, but you do know how many students scored within certain ranges. Check out our new case file. You can see we've got, for example, 8 students who scored somewhere between 9 and 11, 6 students between 12 and 14, and so on. Now, to work with these ranges, we need a single number to represent each one. So we use something called the class mark, which is just a fancy way of saying the midpoint. So for that 15 to 17 range, the class mark is just 16. Simple enough, right? You'll see the process here is actually super similar. First, we calculate the new mean for this grouped data, which comes out to 10.15. Then, just like before, we find the squared distance of each class mark from that mean. But here's the twist. This time, we multiply that result by the frequency, the number of students in that group. This step is absolutely crucial. It makes sure that the groups with more students have a bigger impact on the final number, which makes total sense. So, after we sum up that final column and divide by the total of 20 students, we get our variance. And it is 9.4275. And for our final move, we take the square root of that variance. This gives us our standard deviation of just 3.07. Now, hold on. This number, 3.07, tells a completely different story than our first case, doesn't it? A standard deviation of about 3 is way smaller than the 8.2 we found before. So what's the story here? It tells us that in this class, the scores are way more consistent. They're all huddled up, really tightly clustered around the average. And there you have it. You've successfully solved both cases. That's fantastic work. So before we go, let's wrap up with a few key principles. Think of them as pro tips that you can take with you on all your future data adventures. Okay, these are some crucial tips right from the experts. First thing, if you're ever working with a smaller sample of data, meaning not the entire population, statisticians have a little trick. They recommend dividing by n-1 instead of just n. It just gives you a slightly more accurate estimate of the spread. Second, for most of your deeper analysis, standard deviation is going to be your best friend. It's the star of the show. And finally, what if you want to compare the spread of two totally different things, like maybe student heights versus their test scores? For that, there's a special tool called the coefficient of variation. It basically turns the spread into a simple percentage so you can compare apples and oranges. So there you have it. You now have the tools in your toolkit. You can officially look beyond a simple average and really understand the true shape, the real consistency of any data you come across. You can now tell a much richer, more complete story with numbers. So really, the only question left is, what hidden stories are you going to uncover next? Thank you so much for joining me for this explainer. I really hope you'll keep building these skills by checking out the other explainers we've put together in our Beyond 2025 Math in the Modern World playlist. Remember to keep asking questions, always stay curious, and happy investigating.